This is a video on uh, the general understanding of the correct model of the atom and why we care how the atom, specifically where the electrons are located. By now, you should have printed out um, notes on correct models of the atom, which is right here, and you should have printed out or opened up the a diagram of what the atom looks like. I'll be referencing them. Okay, up until this point, you have been told that the electron resides in, there's a nucleus with the protons and neutrons, and the electrons reside outside in energy levels, and they're revolving around in the energy levels around the nucleus like planets around the sun. That's not correct. The correct answer is called the, and I'll go to the notes now. It's called the charge cloud model or the quantum mechanical model. It's called the charge cloud model because, well, first of all, we don't know exactly where the electrons are located at any specific time. They're in a region outside the nucleus, and they're in energy levels, but where they are in those energy levels, we're not quite sure. Nor will we ever know, nor will we ever care. Okay? So what Bohr has done is basically cut up the outside of the nucleus, the outside of the atom into these concentric spheres called energy levels. But where the electrons are in those energy levels we never know. It's called a charged cloud model because what's on the outside of the atom is electrons, and they're negatively charged. And it's a cloud because the electrons are moving at the speed of light, which is 3.0 times 10 to the 8th meters per second. A typical atom is about 10 to the 8th to 10 to the 9th, that's negative meters long. Instead, in essence, about a nanometer or 10 nanometers wide. So if you assume it's 1 nanometer, in 1 second, the electron will have gone across the atom 10 to the 17th time, which is about a billion billions times. And in 1 second, if you go around or go across the atom a billion times, it looks like you're everywhere. That's why it's called a charged cloud model. The reason why they also call the quantum mechanical model is because, which we'll explain later, this electron acts more like a quantum particle than a classical mechanical particle like you and I. But we'll talk about that later. Why do we care? Well, it's all about Coulombic force. As you know, Coulombic force is equal to Q1, or if you don't know, this is what it's equal to, Q1 times Q2 over R squared. And let me go to the diagram now. So CF is Coulombic force. So Q1 is is one electron. In essence, what's the force, Coulombic force, on every individual electron? Well, there's two things. There's a repulsive force, an attractive force to the nucleus. That's what Q2 is, and that's called the nuclear charge. And if you have more protons in the nucleus, it has a greater pull because Q2 would be bigger, so the Coulombic force is bigger. The other thing, there is an attractive repulsive force, which is electrons and electrons, too. And they exist. What's this R? Well, R is a distance from the nucleus to where the electron is located. And that makes a difference because since the R is on the bottom, if the electron is closer to the nucleus, your Coulombic force is greater. If it's farther away, it's less great. So what happens in an individual atom, there's a counterplay or a resulting force from the repulsive force of all the electrons to each other and the attractive force of the electrons to the nucleus. And what happens is it will eventually, very quickly that is, equalize out, and you get the size of the atom. And therefore, you know how far the electrons are away from the nucleus and where they're located, which makes a big difference because, again, if they're close and this number is little, that makes the Coulombic force great, a great pull on the nucleus. And if they're far away, that makes R large, and there's very little pull on the nucleus. And that's important. Well, for the atom itself, it's important because it basically gives you the size of the atom and how easy it is, how much energy you need to pull an electron away from the nucleus. And we'll talk about that later on. But the big thing is when two atoms get close together. Well, when two atoms get close together, the electrons, and we'll look at the outside electrons, these two here, because that's what actually will move if they need to. Well, this outside electron here is being attracted to its own nucleus, but it's also being attracted to the other atom's nucleus. And of course, then the electrons repel away from each other. So what happens is you get a resulting force of either the attractive forces and the repulsive forces are such that three possibilities can happen. Either one atom pull, its attractive force is so pull, it takes the electron from the other one. Then you form ions. The guy that gets the electron is a negative ion. The guy that releases the electron is the positive ion, called cations, and negative ions are called anions. More later. Or it's not a great difference, and what happens is all the forces kind of are there. Therefore, they're all held together, and that's what you would call a covalent bond, or in biology you call the substance like a molecule. That's why it's really important to know where the electron is, because when atoms come together, they're going to do those two things. There's a third thing called a metallic bond, which we'll talk about a little later on. So there's actually a third thing that can happen. But right now, we won't talk about that. So that's the importance of why you're going to spend a class and a half of me talking to you, or you looking at videos on where the electrons are located. Okay? So that's why we're going to spend all this time talking about the resulting locations of where the electrons are located. Thank you.